Now let's have a closer look into the protocol design, version 4, version 6, and especially the migration from 4 to 6. Some general remarks. Well, you can imagine it's really not trivial to create a protocol that survives many years, more than 40 years now. Many different developments, new technologies, extremely fast computers. No one could have imagined this 40 years ago. So continuous change of upper layer technologies, think of the web and all the hype around all these peer-to-peer networks, etc. Quality of service, IP television, but also lower layer. We had a closer look into terabits per second networks. Still, it's important to know IP version 4 is still the universal glue of the internet. Well, there are some additional protocols needed. We have a closer look and we'll answer some of the questions. So why was this IP version 4 and still is so successful? So still IP version 4 carries a lot of the traffic in the internet, although we have version 6. And why is it so difficult to change the network layer? And how can we live with two network layers at the same time? So you all saw already this hourglass model where you say, okay, we have this really tiny waste of the IP layer 3 here in the internet. We have many different lower layer protocols. Okay, we had a closer look into Ethernet, PPP. A lot is Ethernet today over different media. And we already had a closer look into these application layer protocols, some of them, and we will have also in the next chapter a look into this transport layer protocol. So IP version 4 is the fundamental network layer protocol of the current internet, although we have a new version also since the mid-90s. Basic properties, it's IP takes care for transparent end-to-end communication between hosts. It's not reliable, it's best effort, it's connectionless, it's packet-oriented, so it's like a postcard or letter. Simple addressing, hierarchical 32-bit addresses. So hierarchical, that's quite important. We will see it supports also some more features. So this is how it all started. And we'll quickly go through version 4, because version 4 typically is also already covered in the bachelor level courses. So what do we have? The IP packet, well-known classical format. This is how it all started. So the typical header is 20 bytes, and then data follows. We'll have a closer look into some of the parts, but most dominant here are our addresses, our IP addresses. These are all well-known 4 bytes, and we have some additional fields. So how does it all start? Well, with a version number. So that means, okay, the very first bits will tell you, do we have version 4? Then the structure looks as follows. Or do we have version 6? Then we have later on a close look into this version. Just by the way, there was also a version 5 called Streaming Protocol, ST2, but that has been dropped due to many reasons. Political reasons, but also complexity reasons. There's never some versions 1, 2, 3 used in the internet. So 4 is the first protocol and 6 is then the follow-on, although there was some research claiming version 7, 8, etc. So it starts with the version number, and the next one is then the header length, and the header length is typically set to 5, so this means 20 bytes of a header, because we count the 32-bit words. So the header length depends on the IP options, as we'll see. The options, they have a variable length. Options, they are a bit problematic. I will come back to this. So that was the classical start of an IP packet. And then the following field was originally in history called the type of service. So already from the very beginning, there were some thoughts about maybe we do not always have only best effort, but maybe some more important packets, some less important packets, some delay-sensitive packets. Later on in the 90s, there was a lot of discussion going on. How can we support, for example, more real-time applications, voice, audio, video, with the internet? So this type of service field is now historical, and today it's called, it's a diffserv, differentiated services code point, DSCP, plus 2 bits for explicit congestion notification, ECN. ECN is important for the higher layers, so I will come back to this, but here some more words about DSCP. So, as I said, in the classical IP networks, we had this type of service, some so-called precedence bits, and now we have the differentiated services code points, those 6 bits, and differentiated services. That's one of the models. There was also another model called integrated services, but it was not that successful. So, differentiated services supports different types of service, as the name says, differentiated services. And the important part is we distinguish between different services by looking at the code points. The routers will do this. So for voice, for video, for streaming, for web usage, for file transfer. And it works as follows. Differentiated services defines a so-called per hop behavior. Okay, what does it mean? What is a hop? So imagine you have a router, and then you have one hop to the next router. And exactly this router, at the starting point of this hop, this router decides about the behavior. So if you forward the packet, you follow certain classes. There's the so-called default forwarding, so that's typically best effort, the classical thing. Expedited forwarding, so this is for low loss, low latency traffic, so it's very important traffic, but also with low loss. Assured forwarding classes, we'll have a closer look into this. So we want to describe certain conditions for forwarding, and then that's more the classical precedence fields, the so-called class selector per hop behavior. So the router decides by putting the packet into a certain outgoing queue about the per hop behavior. And the idea is, if you concatenate certain per hop behaviors, then in the end, you will have a service of a different type of quality. So if all the routers do some expedited forwarding, whatever this means in detail, then in the end, we will have a certain quality of service. So this is all based on the principle of traffic classification. So each data packet is classified into one of these traffic classes. So the router basically has different queues, and then the router may insert, depending on implementation, etc., may insert the packet by checking the differentiated service code point in the packet, will insert the packet in different queues, and then there is an algorithm that then picks packets out of the queues and forwards them to the next router. So that's the idea. So what can you do with differentiated services? For example, there's this assured forwarding behavior group. And then we could, for example, define for maybe a video stream, we could define the drop probability and different classes from the highest priority to lowest priority. And then we could say, okay, we maybe have a really high priority stream of packets, and they should also have a low drop probability. Or we could also say, this is, for example, okay, maybe it's important that the traffic gets through, but the drop probability, I don't care. So if something gets through, it should be in time, for example. Be aware, differentiated services does not give any hard guarantees, because it's this concatenation of per hop behaviors that creates a certain quality of service. And then in the end, it depends on the single router, how the router then implements this. There's some more examples, and you see different code points. And this was the old TOS field. Here it's called the class selector mapping, where we have certain mappings, for example, for FTP or SNMP, or we have certain peer-to-peer traffic following other standards, and TPO routing protocols will come back to this. And for all these different types of traffic, you see different applications, we have specified a certain DSCP value, here given in decimals. And then we have also some additional recommendations. You see here, for example, for telephony, that's our expedited forwarding. Then we have a certain DSCP value, or the classical standard, then the value is simply 0, or low latency data. Then we pick one of these assured forwarding classes, AF21, 22, etc., etc. And you see also all the standards for it. So again, the key idea is that you have a sender here, and you have your receiver there, and then you send to the first router your packet with a certain differentiated service code point. Let's say, oh, it's telephony, it's quite important. And then it's up to the router how to handle this packet. And maybe, hopefully, the router has a special output queue, and then the router will then put this packet in the output queue and creates a certain per hop behavior. And then it's up to this router, if the router can also do this. But maybe you have a router in between that doesn't know anything about differentiated services, then, okay, tough luck. The router simply forwards the packet. And then maybe, again, you have a router that knows something about a certain per hop behavior. So it's not a hard guarantee. It's statistically, and the routers, if they can, they try to apply this. If they are in overload situation, they can then give certain priorities. Then maybe first those expedited forwarding packets with a DSCP value of 46, and then they may drop other packets. This could be done, or the scheduler changes and so on. So, but altogether, this creates this behavior along this chain of routers. Okay, but the majority of traffic uses default forwarding, so that is our best effort. But there are some applications already many years ago. Big telco companies offered voice over IP telephony, then using differentiated services. What else do we have? We have the length field, so the total length of the packet, and that's wide limited, so that's the maximum length, also 64 kilobytes, that's the maximum length of a packet. Then we have 32 bits that are quite interesting, so in IP version 4, not in IP version 6 any longer, but in IP version 4, we have a way to fragment packets. What does it mean? So if you have a packet of a certain size, fragmentation means you split up the packet into several smaller packets. For example, like this. So you create 3 packets out of 1. And the idea here is you give the packet a certain identification, and all the fragments then also carry the identification so that you know they all belong together. And I will come back to the offset. So first of all is why? Why doing this fragmentation? Simple example. Look at the setting. Maybe you try to send a packet from here, your computer at home, and you're connected to the internet via PLC, power line communications. So power line, internet via power grid. There you have certain maximum packet sizes, for example, 400 bytes. Then maybe you create your 400 bytes packets. They go through the internet, everything is fine here because typically you have something like 1500 bytes as a packet size around, for example, so that the classical maximum Ethernet packet still fits. Okay. And then you reach here a router, connected to a smart home system, Internet of Things devices, and there for certain reasons we have only a maximum packet size of 127 bytes. That means that the router here has to perform the fragmentation. Otherwise you cannot transport packets in this IoT network. The reason for IoT having smaller packets is typically because we go over a wireless network and you have higher error rates, etc., etc. So there are some arguments for having fragmentation. So for example, you agree that you have on a certain link a certain maximum transmission unit, MTU, how many bytes you can carry as one unit. And typically you have this 1500 bytes. But if, as the example showed, for the IoT network, the outgoing link MTU is smaller, then we have to fragment. So the routers will perform fragmentation. That's the router. The router fragments. But putting everything together, never done by the routers, but at the destination. Why? Well, routers are extremely busy. Routers do only the things that are absolutely necessary to forward a packet. Well, to reassemble the packets, that's not necessary. So you can transport the fragments. For the destination, it's important. Yes, you have to recreate the original packet, not for the router. So the routers will do fragmentation. They don't like it, but they do. They have to in IP version 4. But they will never reassemble, recompose those packets. Plus, there might be problems like dropped fragments. What should a router do, etc. It's not the job of a router. So, example, how does it look like? So you send, for example, something with 4000 bytes because the MTU is 4000, but you're connected here, you see on the last hop, with the MTU of 1500. So 4000 bytes go through the net, but the router here will then split up everything into these 3 fragments. And then forwards these 3 fragments to Bob, and Bob has to reassemble everything. So, what happens to our packet? The original packet with a 20 byte IP header and whatever 3980 bytes payload will be fragmented into these 3 fragments. Again, each fragment has a 20 byte header, so you introduce certain overhead, and then the payload or the part of the payload follows. For the receiver, it's important to identify the fragments to be able to reassemble them. So, all the fragments belonging to the same packet have the same identification field. So we know exactly, ID is 17, then I collect all the fragments with 17. Oh, there's another fragment with 32, then I collect all the 32s. Because a receiver may receive many fragments, also mixed. So there's no in-sequence delivery, could be completely mixed. Then we have additional flags, don't fragment, and more fragment bits. More fragment bits, that simply means, okay, if it's 1, further fragments will follow, and 0, it's the last fragment of a datagram. Then the receiver knows, okay, that's at least the last one, and then can check to have all the others, or at least wait a bit for all the others. Then there's an additional bit, don't fragment. That means, okay, maybe I don't like fragmentation, and there's a requirement that all routers have to be able to forward up to a size of 576 bytes. Everything beyond, that's optional. Okay, so if the packets now are larger and they say don't fragment, then discard them. You don't have to discard, but it could be discarded. Okay, now we know where all the fragments belong to because of the identification. We know which one is the last one, but we don't know how to sort. And this is why we have the fragment offset. The fragment offset tells me where the fragment belongs to. It counts in multiples of 8 bytes. How does this look like? So if we have a certain packet, we start fragmenting it, and you see we have a certain identification and we repeat the identification for all the fragments. That means we know that they all belong together. And you also see, okay, we have the more fragment bit set, more fragment bit set. Okay, not set, so this is the last fragment. And now the offset follows, and the offset then will tell me, okay, where does this fragment belong to? In multiple of 8 bytes. So 0 here indicates I start exactly here. 64 times 8, that's exactly my 512. That tells me I start here at 512. And then 128 times 8, that tells me, okay, I start here at 1024. So that's the idea. So the offset here tells me where to place the fragment. And the receiver then has to wait until it receives all the fragments. And if not, tough luck. No one guarantees you delivery of IP packets. What else do we have? We have the TTL field, time to live. Time to live, well, some people rather say it's time to die. Why? Because you typically set a TTL value at the sender, and all the routers, they decrease the TTL. So the sender sets a value, the routers decrease, and if 0, then you drop the packet. Plus, you send back to the sender a message, a so-called ICMP message. I will come back to this. This goes to the sender. That's needed for many purposes like pings, etc., trace routes, and so on. So the sender sets a TTL, all the routers decrease it, and if it's 0, you drop the packet. Why do we have this? Remember layer 2. I told you that, okay, for redundancy reasons, we have more than one path between different switches on layer 2. That means we have a graph with circles. But if we have circles, packets can start circulating infinite number of times. What was the solution in layer 2? Spanning tree. So to avoid circles, to avoid this, create a tree structure. And we had the spanning tree protocol. That was layer 2. On layer 3, I already told you in the last chapter, it's impossible to have a worldwide spanning tree. So this is why we have the solution of the TTL field. So we decrement, for example, by 1 on each router. This could be handled differently, so there are also good reasons for decrementing 32, for example, at the border of an organization. But at least we decrement by 1. That means if a packet starts to circulate due to loops, because the internet is not loop-free, then sooner or later the packet will die in one of the routers. So that's the idea. On Linux, macOS, Windows, they typically set different values for the TTL when they send something. So we start, for example, with a TTL equals 64. Then we enter this, and if we then have a Then the first time we have 63, and we have 62, and then if we have the circle with 61, 60, etc., until we reach 0. And if we reach 0, we drop the packet and send back an error message. So that's the idea. Okay, no packets that loop there forever. What else do we have? We have some kind of a forward pointer, a protocol field that tells us, okay, what is the protocol used in the data? So we violate a bit our layering principles, because we have in layer 3 some information about layer 4. But this protocol field tells you, for example, if there's a 6, oh, we have TCP that will follow, because inside the IP packet there's a TCP packet or UDP packet. And then we have a checksum, a header checksum, but this is just a checksum for the header, not for the payload. So there's no protection of the payload in IP. The reason, well, it was said that, okay, this should be handled by higher layers, so maybe the higher layers don't need a checksum. Plus, we all know we have the layer 2 checksum. There's already a checksum. So why having an additional checksum? Oh, very good question. So one reason could be, okay, maybe if I insert an error on layer 3, then layer 2 will not detect it, because this is then a valid layer 3 packet. It has an error, but for layer 2, it's a valid layer 3 packet. So, but this is very rare. We'll see what the consequences are. So, but in IP version 4, there's a checksum. And then we have our source and destination IP address. These are those well-known, what we already had, addresses and so on, source and destination. And then many, many different options. Options for recording the route a packet travels. So IP packets, when traveling, they could, in theory, record the path they go along. Or you could also tell the packet, this is called source routing, which way to take. We will see how this is done in reality, but you could, in theory, that was the idea, tell a packet, please first go to this router, then go to that router, then go to that router. This is called source routing. So the source determines the path. Then we can collect timestamps, etc., etc., etc. So many options. What is the problem? So in real world, typically the routers have to take care about options. And I told you already, routers don't like any additional work. Routers perform perfectly if they can do things in hardware, extremely fast, nanoseconds to forward a packet, but not handling of options with variable length, dynamic stuff. So this is costly. No one likes this. You don't do this in hardware, you do this in software, etc., etc. Options also may reveal certain information you can follow by looking at the packet, follow certain paths, then poorly implemented, security concern. So there's a generic advice, don't use options, although they're there. So the question is, are they supported? Yes and no. There are some papers telling you so IP options are not really an option, and there's studies showing that, okay, if you enable the options, then successful packet delivery ranges between 40% and 4%, depending on the path, down to 4%. So that means if you enable options, it's quite a good chance that your packet will never go through. So you better do not use the options. So some implementations and some routers, they support options, some simply forward the packets. So it depends on details, it depends on transport protocols, on which options. So yes, some are supported, but you should not rely on them. This tells us if you cannot rely on some features, don't use them. because you don't know if they are really implemented, and then you get unpredictable behavior, so better don't do it. Okay, some questions. So we looked at the basic format of an IP version 4 header, and there were some, a bit newer at least, mid-90s stuff, differentiated services. So what is the basic idea, and who is responsible to guarantee? Can we guarantee? Well, to give at least a certain quality of service. With a closer look into fragmentation, why do we need this? What is the idea behind fragmentation? How is this done? And then again, now we see, oh, there's a TTL field in IP version 4, but it's not in Ethernet. Well, what problem has to be solved in both layer 3 IP, layer 2 Ethernet, and how is it solved? And then finally we looked at the options and saw there are some problems. Why is this problematic? There are many reasons for this.